We are going to continue the discussion about the memory management. So this is, I think, the main part of the project. So I think if you miss the chapter 9, it will be hard to complete your project. Okay, project 2, I mean. So project 2 is page replacement algorithm. So if you complete this one, the programming itself is not very difficult once you understand the algorithm. So the others are straightforward to implement the page replacement algorithm. Okay, so last class we have talked about the mainly what? You remember that? What was the topic in the last class? It's the main memory management. So the main problem of the memory is what? How to allocate the memory space for what? Process. That is the main issue. So we have discussed about several different approach strategy and algorithms. So today we are going to discuss about the virtual memory. That doesn't mean it is the really virtual memory. So anyway, the main problem of using the memory space is it's very limited. Okay, if we, as I mentioned many times, if we have the unlimited resource, for example, the unlimited size of the memory, we can just allocate the process to any memory space. So we don't have to worry about the contiguous allocation, dynamic loading. It doesn't matter. We can just allocate the memory. However, the first reason, the memory is expensive. Okay. Also, it's limited by the addressing. So we have the limited memory space. So we need to think about the alternative way, that is based on the virtual memory. Also, sometimes it's called the swap. However, the swap is not the virtual memory space. The long time ago, swap means we can replace the process by process. Okay, so in case we need the free space on the memory, but if not, if there is no available space, we can swap out, which means we can unload the process from the memory to hard disk drive, then load the new process to the memory. That is called the swap in and out. However, swap in and out is not used in current operating system. Why? It's a very expensive operation, especially to access the secondary storage hard disk drive. It takes a long time. So no operating system nowadays use the general computer operating system do not use such the swap operation. Instead, we discuss about the different data structure to address such an issue. That is the paging. What is a page? Did we? I think that we did before. What is a page? Page is a fixed size of the space in the memory. So we are going to consider program as what? Memory. Okay? And also physical memory. So because of that, we call the program as a logical memory. Then the physical memory is a physical memory. Then divide by fixed size, the data structure, like the 512 byte or 1K for what? Logical memory and also physical memory. So to differentiate such a logical memory and physical memory, the page in the physical memory is called the page frame. Okay, we have a number of physical frame, and also if you execute the program, we consider program as the logical memory and divide by the page size. So we have a number of the page. The next problem is how to map. Okay, how to map from one to the logical memory space, logical page to the physical page frame. Which means we need to know each logical page map to the page frame, physical memory. So to do that, we can manage the mapping table. So using the memory management unit, the MMU can be implemented part of the memory or hardware. So we can define the physical address for specific instruction. So CPU can access the first MMU, then find the physical location. So I think that we didn't have enough time to have a quiz. Okay, so anyone who do not receive the quiz yet? The GA? Where's the GA? She's outside. Why don't you ask him to come in? So from now on, so if you already received it, I will give the 5 minutes. Okay, why don't you solve the problem? That is the how to map the logical pages and the physical page frame. Okay, solve the problem. Why don't you raise your hand if you do not receive the file? Also, if you missed the last class, let me know. I will give the new one. So I will give the 5 minutes. This is a real quiz this time.
What?
Okay, this is a quiz. I will give the 5 minutes. Because last time, I'd like to have the pop-up quiz before I end the class, but I forgot the time, so we couldn't.
Are we allowed to use laptop?
No, just I already explained that right now, so you can solve the problem. Do not use the computer, so I believe you can solve the problem. I will give the hint instead. Required. This is a test. Okay, this is the example. This is a test. Do not use a computer. Only using this slide. Why don't you solve the problem? Do not discuss. You don't have to discuss. It will be considered as a cheating. Those who missed the last class, raise your hand. I will give the news, the quiz sheet. In this case, page size 8, but this slide is a 4 byte. That's the difference. Okay, there is a mapping table. The page table here, 1, 0, 1, 2, 3. That is a logical, the memory, your program, and the frame number is a 3725. Okay, then find the physical address for the given the logical address. Chapter 8. Do not use computer, as I said.
I can see that slide.
Then you can come to here. This is a test. Will be great.
Excuse me, logical address is pages, right, or not?
Logical address is in your program. Here. So last one is only for attendance. This one need to grade. Do not check the attendance. don't have to discuss. Please close your laptop. And also, you did? Close your laptop. What's the size of this program?
8 bytes.
24 bytes. It's 4 pages, and each page has the 8 bytes. It's for a 24, right? So 24 bytes is this program. Then your physical memory size is, I think up to based on this, it will be 64.
64.
Right? So at least 64,
Yeah.
right? There is a tricky question that is 30. 30 is out of range of the program. Then what happens? Please do not discuss. Five minutes. I should have pop-up quiz the last time, but I forgot the ending time. So are you recording? This also? It's okay. Two minutes? Okay, so that's it. Why don't you collect? Why don't you submit it? Okay.
Understand these simulation. Okay, so I'm not the only one. Also, I think I am down.
Okay. Let's solve the problem together. So page side is an A5, and this is a table. 0, 1, 2, 3, 3, 7, 2, 5, and first 3. So I think the first thing you need to understand is the concept of the what is the virtual memory. What is the page, what is the page frame, what is the logical memory, what is the physical memory. Logical memory means your program. So in this case, the program needs how many pages? 0, 1, 2, 3. So 4 pages. Okay? So 0, 1, 2, 3, each one has 8 bytes, which means so 0, 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 15, 16 through 23, 24 through 31. This is your program. Okay? Then this one mapped to the physical memory 3. Physical memory how many? So we are not sure whether page frame number 8, 9, 10, but in this example, at least 8, which means so this is 0, 1, 2, 3, 4, 5, 6, 7. Okay? And this one, physical memory address is 0 through 7, 8 through, this one is 15, 16 through 23, and so on. Right? So for example, this is a logical address 3. That means that this one. Logical address 3 means page number 0 and offset 3. Okay? So, where is the 0? Is the 3. 3 is the 24 through 31. And what is the offset? Offset 3. 24, 25, 26, 27. So, this is going to be 27. Right? Then, I don't have to do the other. Except, what about the 30? 30, do you... in this case, we have, what is the program? So, 1, 2, 3. 30 we have. Is there anyone? 30. I think there is we can compute. So, what about the 33? Or we cannot find, right?
Yeah.
So, in that case, it's a 12. In case this is not in between the base and the limit address, so that will be 12. Okay? I thought that is out of the range, but it's okay in this time. Okay? Any question?
But can you just give like the whole answer without going?
Full answer?
Yeah.
One more. Okay? Which one? 19. For example. Okay? 19 is here, right? Page number 2. Offset is 16, 17, 18, 19. That is a 0, 1, 2, 3. Offset number is a source of 3. Okay? So, am I correct? 16, 17, 18, 19. So, 0, 1, 2, 3. Yes. This is a 0, 1, 2, 3. Yes. So, virtually 3. interesting is the same. So anyway, page number 2 is the 2. So that is this one, right? Then offset is 3, 16, 17, 18, 19. That is the 19. So physical address is the 19. One more.
Yeah, let's see.
The last one, 10. 10 is 8, 9, 10, offset, page number 1, offset, 8, 9, 10, 0, 1, 2, it's a 2. So 1 is mapped to 7, this one, and this one is 31, 32, 40, 48, what is the next? 48, 56. 56, and offset is 2, 0, 1, 2, 56, 57, 58. So this is a 58. Okay? Don't be frustrated.
I mean, I was just following like the equation.
Yeah, this one, equation, using equation, you can, instead of this one, you can change it to A,
That's what I
replace
did.
by A. This one is depending on the page frame number.
That's what I did, and I got different values.
But this is just an example of in this case. So each one has different page table. We don't know where it goes. Okay? Once you detect find this one, you can multiply by A. Okay? Page number. But so I'm going to ask the exactly same question, but with a different page size and different page table. Okay? In the final exam. Okay? This is the one of the worst. The average question based on my previous experience. Okay? So please, once you understand the logical address and the physical address, the memory and physical memory, it's very easy. It's just a simple math. However, so sometimes it's not, because I guess it's my understanding, the name itself is the virtual map and something, the logical memory. Okay, it looks like something memory structure, but is it true anyway? The process is going to be in the memory. It can be considered as a memory structure. Okay, so this is the concept of pacing. We are going to I'm still struggling to use the new device. I'm a little bit disappointed because it's just the reason why I select the surface is it's too simple and light to carry on, but I need to carry on the cable and something connector and variety of things, even the pen or the mouse. So more complicated. So I'd like to go back to the old style. The last one, my laptop had a power fan problem, so it's very, very hot sometimes, so it's automatically shut down. So today, we are going to discuss about the alternative way to manage the memory space, which will be based on the page. Okay, so what was the solution in case the memory space is full and there is a new process executed? So we can swap in and out. However, as I said, that is a very expensive operation. Not many of current operating systems adopt such an idea. Then, what other strategy we can use? In case of full, we can use dynamic loading. Dynamic loading means, so when you execute the program like this one, logical memory, do we need the entire instruction? No, we need first, anyway, the first page. So why don't we? The page that is on demand is called the dynamic loading. So we can address the memory problem reasonably, but not fully. Because anyway, eventually we need sometimes all the process pages, but sometimes we have the limited space of the memory, so we cannot accommodate this one. So today we are going to talk about the alternative way how to manage such a limited memory space, which is called virtual memory. Okay, so have you ever heard of it? Yes.
Before you proceed, just a quick question on this.
Yes. Quick question.
Yeah. You see, the first example you gave, the logical address is 3.
Yes.
So you went to the logical address, right?
Yes.
In
3.
In the table.
Yeah. Table 3.
0, 1,
That is
2,
a
and 3.
3.
So you said that that's a logical frame, page number is 0.
Yes.
So you're referring frame 3,
So 3. Yes.
right?
Uh-huh.
And then how did you get 27?
The offset is what? It's 0, 1 to 3. Offset is 3 from here. 0, 1 to 3. In page number 0, offset is 3.
Yes.
Because physical address is 3.
So
Offset
the
is
offset
3.
is the same.
Yes.
So in the case of 19,
19 you need to find here, and
That is
offset
also-
is 0, 1, 2, 3.
okay.
So from the starting point of each page. Okay? Then entire page move to here, there, here, that physical address will be changed. We don't know where it goes. We have seen such a problem in the addressing. So that is the reason first when you code is a symbol, integer I. Okay, it doesn't specify. Okay, physical location. Even compile, after compile, your binary code cannot specify the physical location. Instead, it's a relative location, which is called offset. So we can use until it's loaded, we don't know physical exact address. Okay, so that is the physical address. Okay, so let's go back to the main topic, that is the virtual memory. Have you ever used the virtual memory on in your computer or laptop? Yes. Go. Where?
The back computer, I think there is a citing, probably there is a citing side.
Uh-huh.
Set up the virtual memory.
Yes. If you go to the property of your computer, you can change the size of the virtual memory. What does that mean? Size of the virtual memory determine what?
The memory in hard disk.
It's the memory in your hard disk drive. What's the recommended size? The bigger is the better? Usually not. Probably not. So usually it is recommended the 2 times of your physical memory, then it can be the best performance. Then, what is the purpose of such a virtual memory? The physical memory is not enough, so it's kind of an extension of the physical memory structure. Anyway, so whenever we talk about the algorithm or the functionality in operating system, not only operating system, any subject in computer science and computer engineering, that is based on data structure. So memory has their own data structure. What kind of data structure memory has? It's an array of bytes. Basically, it's an array of bytes. Nothing but array of bytes, really. Okay? Is there any specific sector or the cylinder like the hard disk drive? No, it has an array of bytes. However, such an array of bytes is not efficient way to read and write the data. So we consider what? Page last time. So we have the fixed size of the data structure. Then the data structure, such a page data structure, can reduce external fragmentation. Because we have the fixed size, smaller size, we can allocate the different number of we can allocate like this one, not continuous, the memory structure, it can be anywhere. So we can remove such an external fragmentation using the page. Then, why don't we extend such idea? So because the memory, physical memory, anyway. So in this case, it's enough. However, what if we have 10 processes? It will be a lot of, even definitely we need more and more the physical memory space, which is not enough. So the only solution is swap in and out. Instead, of the such a swap in and out, why don't we extend such a physical memory structure to the hard disk drive? Which means physically it's a hard disk drive, but logically it follows page structure. Then what is the benefit? We don't have to swap in and out entire process. Instead, we can change the slightly location. In terms of logical, it's the both. This is the memory structure. But instead of the allocating from the hard disk drive, it's actually the physically hard disk drive. It's a program, but at once it loaded using the page table, loaded, then in case we need to access, we need to space from the physical memory. So we swap out the specific page to virtual memory space. Okay? This one follow the same data structure, page structure, but physically located in the hard disk drive. Benefit, we don't have to swap in and out entire process, just page by page in and out. That is the resource management issues when you check the the resource monitoring tool always issues how many times page in and out, page I/O, input and output, that determine the performance. Instead, the swap in and out is between the physical memory and virtual memory space. So even though you have the bigger size of this one, you cannot get the linearly increase the benefit. Why? Because anyway, this is located in the hard disk drive. But you can remove some overhead that happen in the swap in and out. That is the virtual memory. So we will see how we can implement such a thing. Okay. So virtual memory is a separation of user logical memory from the physical memory, then extend to the hard disk drive. That's the virtual memory space. Sometimes this space is called nowadays swap space. So swap space does not mean really swap operation space. It can be used for virtual space. It's a swap out for page, not entire process. Okay, so that is the, also at this time we can share the specific pages by the several process like the shared library, system library, input and output, IOS list, or something, the object file, which is shared by the many process that can be loaded in the physical memory. It can be shared by several processes. If they are not used, it can be page out to the virtual space. So that is the idea. Also, it can be used for such a virtual space can be used for creating the process. The creating process. How can you create the process in operating system? Fork and exec. What does that mean, fork? Fork means copy. So I'd like to create the process, which means I'd like to copy my memory structure, memory space, the memory data, exactly copied. Then once the child processor changes the data, then it will be separated. That's exec. Okay? That is the creating process, which means it requires input and output in the memory. So it takes a time when you create the 1,000 or 10,000, the process for operation. So why don't we create the space first in the memory? Then if somebody asks the new process, then at that time, instead of the creating or locating the new page, just assign that area. So at that time, we can actually improve the performance to create the process. That's the page pool. So you can make the pool, reserve the space for creating the process. Okay. So that is the virtual memory idea. So it will be similar, just like the main memory management is a demand paging. So whenever the specific page is needed, it's a page in. If not needed, is a page out. Okay. Also, as we have discussed before, we can make the segmentation. What is a segmentation approach in the main memory management? We can make the group chunk of the process. Similarly, we can make the chunk, the group of the pages that are working together. Okay, that is the paging demand segmentation based on the virtual memory. Okay. So to address such a problem, so limited size, the space of the physical memory because of the size of the process. Also, to support the high level, the high degree of the multiple programming, so we can use such a virtual memory. Okay. So this slide shows the diagram. What is this? This is the program, your program. Okay. Virtual memory means this is your program. Okay. It's the page number of pages. Then map to the physical memory. Then virtual space, virtual memory space. Using this one, you can in and out. This one, logically operating system consider the memory space. However, physically, it's located in the hard disk drive. Anyway, it needs input and output. So the number of pages in and out is a good indicator how much faster your operating system is. So page in and out is used to determine whether my operating system has good performance or not. Okay, and also the virtual, such a virtual space, this is a general structure of the process as we have seen before. The stack area increases from the high address to the bottom, top to bottom, and the heap size is increased from the low address. So this area, actually when the process is created, it's not used, right? So we don't have to allocate this space first. Instead, we can use such a data for shared the memory, or the once it is needed, like the increase the stack area, the temporal data, then allocate the page. That's the idea of the using virtual virtual space. Okay. Why do we need such a complicated process? Anyway, due to the limitation of the memory space. If we have enough memory space, we don't have to. Since to save the space, we can consider this one, the in between the stack and the heap area is not used at the first time, so it will not be allocated. Also, in case of the shared memory, shared library, such a shared information part will be based on the pages.
Okay. So what you're saying is that every time when the memory is less, operating system picks the virtual memory which is part of the
Actually, not when you need, it's always the operating system uses the virtual memory space.
Okay. And you're saying it is on the hard drive.
Yes.
So is it a little slow then compared to?
Oh yeah, it's slow, but faster than the swap in and out. Okay, swap in and out is you need to change the data structure also. But for the operating system, you can consider virtual space as the memory space. But in between your main memory and the virtual memory space, you need to in and out. That is called the page in and out. That also need input and output. However, that is faster than the swap in and out. Okay? So that is the different thing. Whether you consider paging, the logically is to consider the same data structure or not.
So then swap in and out, where does it happen? In the memory?
The swap, from the memory space, you can just download everything to the hard disk drive. Actually, you remove just to save the current data, change the data, and download and upload from hard disk drive to a new process. That is a swap in and out. However, in this case, instead of terminating your process or the context switch, you can still keep the current process, but page by page, you can in and out. That is a different thing. Okay? To speed up. Okay, so in case of the demand paging, so once we need certain, so for example, in this case, we have the two programs, program A and program B. So in case we need the pages from the virtual memory, they can be swapped For example, in this case, process A is running, process B should be run. At the time, you can, if you swap out, means so you can the page out that can be saved in the virtual memory. Okay, then you can bring the new pages to the program. Okay, that is what I explained before. So that who is in charge of such a thing is called a pager. So pager is the part of the operating system who can manage the which the page will be out, swap out, the page out, and which the page will be swapped in, the page in. So that will determine. So in your project B, second project, you will implement this pager. In other words, page replacement. Okay, you will implement such a pager. So that means we are going to discuss about the algorithm used in the pager. Okay. Also, this pager maintain the table between the page table, so logical memory, and the physical memory, so page frame number, and also whether that is valid or not. For example, this one, program A is in the page table, but in case swap out, which is not available. Even though they are in the same data structure, memory structure, it's a virtual memory structure. However, from the CPU, it's not in the physical memory, so cannot access. That time it can be set as I, invalid. Invalid means it's not in the physical memory, so which means, so if you want to access such a data, so in case of the invalid, it's a trap, then bring such a page into the physical the memory space. Then it will be changed as the valid. Then finally, CPU can access, processor can access the data instruction. So this slide shows how it works. Okay, then we have this one. So, for example, so we try to load the specific page from the CPU. Okay, then the first need to check the page table. So already executed. So CPU expect such a page is on the memory. But when we check the page table is invalid. Invalid means it's already page out. It's in the virtual memory space. So we need to bring that the page into the physical memory. Then at that time, so which means at that time you need to find the free frame, page frame. We will talk about the details how to find the free page frame. That is the key part of the pager. Then once we find the free frame, that load is a swap in terms of the page or page in. Then update the page table, and the page is valid. Then ask the CPU. During that time, CPU does not wait until it is available. Instead, it will process other process. It's a context switch. So to continue this one. At this time trap, so process other. Then once this is updated, set up as the valid, then it will be waited in the ready queue. Then the dispatcher, the CPU scheduler, will select the next time. If that is selected, then go ahead. Okay, this is overall.
Why was it invalid and how did it become valid?
Invalid means what? It's already executed, so CPU expect such a page is in the memory, right? But unfortunately, this time, in case what is an invalid? Invalid means the page is not in physical memory but virtual memory. Okay, which means CPU cannot access such a page. So how can CPU access such a page? You need to upload. For example, in this case, CPU would like to access A is already given. D, David, you need to access. You need to load the page D into the physical memory, then change the value. That is, D is 3 is invalid, change the 3. Then this process state is going to ready queue. Then once the scheduler select this process, then CPU next time can access this one, then at the time this page is the value. Okay? So at that time, if you can find the invalid page, that it calls the trap. The trap means it's a stop and do this pager, activate the pager. And during that time, the CPU can process another process using after the context switch. Okay, so that is called the page fault trap. The page fault, the number of page fault is another the indicator of how much the good your system performance is. So number of page fault is another the things you need to check when you manage your operating system. Okay. So demand paging, so we already discussed. At this time, so when you are using the demand paging, so one possibility is, so you can consider locality of the reference, which means if the process, you can put this process, for example, this is your program. So this page, it can be anywhere. However, so there is a higher probability, high chance they can work together, which means once this page is used, then next time this page. If you know such a characteristic, you can kind of consider they are work together like the segmentation. Instead, if you do not use a segmentation strategy, you can consider this one put next to each other, work together. Okay, that is called the locality. So you can consider locality to improve the performance. So we will see such a locality, evaluation, something experiment, whether such a locality of the reference helps the performance or not later. Okay? But the problem is it's very hard to find which pages are working together with which pages, right? So but there is a software to automatically analyze. So based on the several execution, you can find that this page are working together. So you can, the operating system pager put consider such a locality to increase the performance. Okay. This is just the staging for the demand paging. Okay, so you can understand. You go through the step by step. For example, first the trap, then the context switch to save all the register information, the current process, and then page 40, if you cannot find in this case, if you cannot find the page is invalid, it's a page 4, the trap. Okay, then check the virtual space and load it. So at this time, you need the overhead. So that is the system overhead. Okay, that is the reason it page 4 to determine your operating system performance. Okay. Then the others are straightforward. How can we measure such a performance? So we can consider the page fault rate. So page fault rate, one means the every time is a page fault. So you need to load the page from the hard disk drive, virtual space, to the physical memory, and that is a percentile, the 0 to 100%, which means 0 to 1. Otherwise, it can. So the 0 means yes, 1 is the all pages page fault. The 0 means no page fault. You can find all the pages from the physical memory. Then, in case of the no page fault, which means the P, page fault rate 1 minus P, this is the memory access time, the overhead. Then in case of the page fault, it's a page fault overhead plus swap in and out. Swap in and out is a page swap in and out, the overhead between the physical memory and the virtual memory space. So for example, if the memory access time is the 200 nanosecond and the page fault service to the latency is 8 milliseconds, it's huge, much bigger than 2 nanosecond, then at that time you can calculate the estimated access the EAT's access time, effective access time. So, for example, in this case, 1 out of 1,000 case, page 40 is 0.1%, the page fault rate, 1 out of 1,000. Okay, at the time, so you can calculate the effective access time. So, how can we get the benefit of using the virtual memory space to create the process?